these wind fluctuations have. So this is how we started Geoscope. Very quickly here, I'm going to share my entire screen. There you go. And yep. So this is how we started with Geoscope, with these renewable energy operators. And our core was to develop a technology so that we can forecast variables such as wind speeds or radiation, temperature, relative humidity a year ahead, or also offering climate services which are based in climate projections, which are projections of the climate and the impact of climate change, 20, 30, 40, up to 100, some models. So those two services are the ones that we are delivering nowadays to the company, to different companies. We have been working in a number of projects, and the cool stuff is that clients are from all around the world, and so we have had the chance to work with very different climate regions or very different types of climate, which was interesting, mostly with renewable energy, but also for other companies like fast-moving consumer goods industries and agriculture. And that's the team. I'm on the top left, Joan Saladik, and here you can see a platform also that we are developing, an interactive platform in the middle. Let me hide this now. In the middle. Shall you have any question, you can visit our website, geoscope.tech, or you can contact me at jsaladik@geoscope.tech. Now, about today, please, everybody, that you have had access to the share folder, and you integrate this share folder or this share directory into your drive, or you download and upload again, download and upload the files, okay? Is anybody having problems with this link? Nobody? I assume that silence is like we are good to go. Well, in any case, let me show you what we have in this link, just to make sure, because I'm also a teacher of Python, and in some cases nobody says anything, but then when I ask for the links, problems are coming. So here we have the link of the. Can you see my browser? Here we have the link, and if we open it, there are some files, 2 free data files, which are end with NC, and a notebook. Now you can do 2 things. You can make a right click here, and you can add this file to your drive, which is this instruction here, add shortcut to drive. Or you can, I believe, just download them all, download them, and then you upload them to your drive. Again, it might take, well, it's not that much because those are netcdf files in the end, but it might take a couple of minutes because 1.54 gigabytes, it's not that small file anymore. So make sure that you have this. I'll give you 5 backup minutes, and 5 backup minutes so I can introduce today's session. So please prepare the files in the meantime. And today's session is going to be about the impact that climate and that climate change is having on renewable energy. Now, you might all be aware but just to make sure that nowadays on Earth there is an anomaly which is generating a positive trend in temperature, which is called the climate change, and this anomaly is happening. These next two free slides are from Surfax. Actually, it's important to say that. And in this first slide, what we can see is that's a plot that we'll do some plots like that actually today. So make sure that you understand them. In the x-axis, we have years, or we have time, and in the y-axis, what we have are values in the case of the anomaly, a negative anomaly and a positive anomaly. Okay, the black line is observations, or is the true weather. And then what the science have been demonstrating is that if the blue line is what corresponds to the concentration of GHG gases due to volcano activity, plus one of the first formulas of climate modeling, the impact of the sun on Earth, which is this blue line here, you can see that the black line and the blue line have been deviating quite a lot, and more especially for the last 50 years, 70 years actually. And now, if we make another line, which is the red line, which includes human impact, or the anthropogenic impact or effects, which are directly the human greenhouse gases, okay? What we can see is that this modeled red line is more correlated, or is more similar to what we have observed for these last 50 years. This means that, well, that climate change is, let's say, quite an evidence. And this is for temperature. Okay. Now, this also can be directly observed, even that would be just an assumption, but it's an assumption based on an observation in terms of the Antarctica, that for the last, let's say, 10 years in this observation, or maybe the base point is the average, or the typical area for the period between 79 and 2000. So this is like, it's 9 a.m., still sleeping, 21 years, there you go. For the last 10 years, the shape and the area has been reduced significantly. And here we can see how the shape of ice is every time more smaller and smaller. So that's kind of another evidence, or another assumption that would correlate with the first one. Actually, when we're talking about climate change, we're always talking about ice, precipitation, and temperature. Let it be frost days, let it be heat waves, or whatever. Temperature and precipitation, mostly. And this is where we started. Why don't we just go a step ahead, and we start talking about wind, and about solar radiation, or relative humidity? So today's workshop, actually, we will not be playing with temperature, and we will not be playing with precipitation. We just have wind data, and we just have solar irradiation data in different data formats. Some of them are like regional data, and some other are just like a single pixel, a point of data for a given area. Okay, so it's time to practice. Any questions so far? There you go. Okay, so if no questions, that's amazing. I didn't know I'm that good explaining myself. And now it's time to open the notebook, double click on this notebook, ECEMP 2022. that you have downloaded. Double click it, and you will have this. Is everybody with the notebook ready? Meantime, please run the first cell because it's going to take long, actually. Okay, so make sure that you can run this first cell of data. You can press the play, or you can just Control Enter or Shift Enter. I just press the play here and make sure to run it. That's very important because, well, if that's the server of Google, we're making sure that it doesn't pay off to have free servers. We are installing and uninstalling a lot of things, actually, which we need so that we can make some cool plots. Actually, yesterday night, I was validating the notebook and I saw that recent changes in this Python library. Nowadays, they are working with the 5.0.0 version. And I could not use Xarray because of these recent changes. So what I had to do is to add another line, make sure that you have it, but I think so because I changed it too, which is uninstall the import lib library and install an older version. Okay, so when you work with this kind of high-level libraries, of high-level Python libraries, you used to have these problems, actually. Like Xarray or Car2Py, for instance, that you need a lot of low-level libraries or background scripts, which usually are not ready. So a lot of red and yellows, no worries, everything is good. Car2Py is being installed, that's great. This means that we are already here. So we are with the last, and now we are importing. There you go. So in my case, I'm ready to go. Let's just make a quick test for Car2Py, and then we can ask to Car2Py which is the version that we have, and the version should be 0.19 post 1. Sounds weird, but no problems because this is what we were asking for. So great, we are good to go. We are good to go. And now in this line here, what we will do is to run it. And I already imported because I was testing everything this morning, but it is for you to make sure that you have your collab, if you upload your files to Drive, connected to Drive. Another way that you could do that, you click on this icon of a directory or a folder on the left. Click on this icon. And in here, you can just directly, I don't want to share the information I have here, but you can drag, let's say you can drag any file here. So if you want to see, for instance, here I have some sample data that you should have. I have import pathlib, which is the standard manager of Python. And here we go sample data. Let me ask him, is that a directory? Yes, it is, sir. That's good. So if you import your data here, whatever it is, .nc, you just have to put this line, okay? And you will have your file, for instance, okay? If you just drag it here, it's going to be temporary access, but good to go. We just need it for 1 hour and a half, okay? Now, here we are then. We have everything here. In my case, my working path or the data is in this, which is from my Google Drive. Let me just validate it. Actually, let's validate it here. It's called Day3. and iterdir, and here we go like list, because let me make sure that's shared. Yes. Yes, there you go. Here we have the files. Okay. So you can have your files in Day3 if you integrated your collab, or if you just simply drag the files here, then you will have them like here. Okay. Well, actually, you will have them like this. Whatever my file is .nc. They are all NC. Yes, so it could be like one file. It's going to be one. Okay. Okay. Great. Regarding the files, anybody knows what is ETA5? By the way, anybody can in 5 seconds explain what is ETA5? Please go ahead. Nobody knows? Okay, and let's see what's ETA5 then. Here I have my data there, and I'm gonna add in this data there all files which end with NC, because I have seen that there is also the A notebook. Okay. Now, this, I'm gonna make it a list, and I'm gonna say that this is input files. Let's call it input files. Okay. Now, my input files looks like this. 3 files. And the first one, it's going to be always whatever the netcdf file is, ETA5. That's great. Now, from here, we will start using xarray. Remember that we import xarray. Oh, sorry. Do you see the screen properly? Because maybe I should zoom in. I remember that depending on which screen I'm sharing in which place, Teams or Zoom, it's very small or very big. Do you see the screen properly?
Looks okay, but maybe after you type something, give us at least 20 seconds or something to type it to
Okay.
go along.
Okay, that's a nice feedback. Much appreciated. Thank you. This means that you at least are interested. Okay, no worries. I'm just validating, but yeah, I'll give you a few minutes when, or few seconds when it's really important. Making validations even for me, because I'm just doing everything from the scratch. It's like a white book for me to a white page. Xarray is called XR. Here you go. Xarray, and we have to use open data set. There you go, open data set. And here we say engine, that's a default argument, it's needcdf4. Needcdf4, actually, I'm going to write here .nc files corresponds to netcdf4 data. Okay, let's run this. Control Enter. Now we are loading a gigabyte of data, and here we can see what we have. And that's a custom file that I'm preparing, so it might look different from the typical netcdf files, and this is because that's the ones which comes from the workflow of Geoscope. So the spatial reference is something we have for front-end guys and things like that. But the most important thing here is T2M, which is surface temperature, or temperature at 2 meters height. That's equivalent to surface temperature. Actually, we can see here the values. No, we cannot see the values. Well, it's just saying I have 4 million values. Dude, I'm not gonna plot you. I'm not gonna show the values. Okay, makes sense. No, we understand you, Xarray. So here we have 4 million values. What are those values about? Let's store this variable in Python like DTS. Now, we also imported matplotlib, which is the most common plotting library, as PLT. Great. We know that DTS contains a variable that's kind of a dictionary, which is called T2M. Now, T2M, it's got to be kind of an array which has the shape of 122,000 values, which those are like time values, 44 latitude, and 76, that's longitude. What if I plot the first one? The first value here. What if I plot it? Let's see what happens. PLT, a quick plot in show. And I'm going to put here, just in case, data. Oh, there you go. We have something that looks like Europe, actually. I'm going to comment this because I want to be loading this every time. Debug. And this looks like Europe. We know that that's temperature. We know that that's like the first day. And it ranges from, let's put 2052 up to 252, sorry guys, up to 290. So those are, any suggestion? That's temperature. Any suggestion? What's this? Degrees? We are burning? No, that's kelvins. So we could go like minus 276, 73. And here we should have it like in degrees. Germany is cold. In Spain, it's not that cold. Woohoo! I'm Spanish. That's good. What else do we have here? We've got the time variable. Oh, and look, that's from 1979 up to the end of the year 2020, about a year and a half ago, almost. So we have data for every 3 hours for the last 41 years. So we have data for the last 41 years temperature for every 3 hours. Okay, that's good to know. That's for temperature. Yeah. But what about wind, which is the most important one, or the ones that we want to work? If we go to list, we will see that wind is WS, and it is in the position 1. Okay, so 1 actually because Python starts counting from 0. So that's 0 and that's 1. So here, if I just change the name, because as in Geoscope, we are very, very ordered and very clean on that, we always put the name of the variable in the path. That's important. I just put WS and I just run this. What I'm going to have, it's loading DTS, now it's plotting, it's the wind speed for period or at what time. Since I am taking the first element, I just go like 0 time, the first time. And this is for the first day of 1979. It's a wind speed night. Okay, that's a model. That's a historical model. They are called reanalysis model. Good to go. That's good to know. From here on, what we'll do is to say, look, I'm going to scroll down now, but look, the number of wind be offshore and onshore, it's been growing and growing and growing. And nobody is taking into account the climate change, because they are just take it easy. I'm not going to explain the industry and their problems, but to make it easy, they are just basing themselves in economic information, not in climate information. Now, is there any climatologists here? No climatologists, okay. Somebody could assume that wind speed could be kind of constant, which says, okay, so for the next 20 years, I can assume that this is going to be this is going to be kind of the typical month of January, because of January, and it'll be like this every year. Okay, now let's validate this theory actually. Let's calculate the average wind speed. Okay, I'm gonna silence and DTS of wind dot group by a pandas operation. You know what's pandas? I believe it was group time, like a quarter. A group by time, like quarter. And let's see what it says. Okay, it's grouping by quarter. And here's yes, I have 4 groups. And since it is a quarter, it's going to be the first group is January, February, March. The second group is like April, May, June. So it's just 4 groups, the quarters of. From here, I can just say, okay, and average them, calculate the mean in the X time. Okay, so since I'm grouping by time, by quarters, I want to calculate the mean in the axis time. Let's make sure that I'm not forgetting anything, but looks that we are good to go here. And that would be kind of the seasonality or climatology. So here we can say, I'm going to share this notebook. So if you cannot copy everything, no worries. I'm going to share this notebook by the end of the session.
Quick question, if I may. If you use mean, quick question, if I may. If you use mean, don't you get distortions by storms? I would have used median.
That's a very good point, actually. That's a very good point, because mean is a Weibull distribution. So a mean is going to be always biased. And I like a lot your point of view. Yes, we could use median, but for the sake of the demonstration, I just wanted to say use the average and use mean for guys. But of course, look, we can do this. We can put here median, I believe, and it's going to be same. Yes. So in the end, it's averaging, but that's a very good point. Completely agree with you. Wind climatology, which is the average for every 3 months. Also, usually climatology you calculate from December to February, so you start in December. But for the sake of demonstration, I'd rather take the quarters, which goes from January. So every quarter will be something like Jan to February, March. March, April to June, etc. Okay, let's see how this climatology looks like. So here we have a X-ray data set, which has 4. Before we were having like, I don't know how many hundreds of thousands, and now we have 4, which are 4 seasons average, latitude and longitude. So we could go like, okay, from 0, which is going to be January, February, and March climatology for the first quarter, plt.show. And here we have the average wind speed for the first quarter. Yes, so that's climatology. Now, one of the assumptions that in the industry are being done is like, okay, to put it this way, I will calculate my climatology. Okay, instead of for the whole time series, I will calculate it, let's say, for a given period, which will go like from 1977 to the year 2000. So we have like 20 years of climatology and then 20 years of deviation to see the deviation of wind speed. Okay, how do we do that? Let's go. If we take this and we select the time and we transform this time in a date time object, and here we have a date time and we select the years, singular, I guess so. Yes, here we have the years, all the years. And then we say, okay, so I want these years to be smaller than smaller or equal than 2000. And that's kind of a Boolean. True, 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 when it is smaller. 1977 is smaller. False, false, false when it is not. Now I take this and I say, okay, here I'm going to say DTS historical or DTS clean, and it's going to be DTS of wind speed this period. Now DTS clean, I'll replace it here, wind speed goes here, and this is going to be, yep, quarter must not be empty. Sorry guys, let me double check something. DTS clean looks like
You are missing a 0 in the year too.
Yeah, I'm missing a 0. Wait with it. It's this here. DTS the time. That's a Boolean. 1 second. Yeah. I know what is happening because I should. I'm applying a group by, so I need to keep that dimension. If I do it like this, it is being cropped. No, it is not being cropped. So wait a second. Boolean array is this. That's the Boolean array. Okay, now DTS, the WS of WS is this for my Boolean array.
You are still working with year 200, not 2000.
DT, I'm still here. Okay, this 0 here. Oh, now I got you. Sorry. I was not understanding. Okay, this 0 here, and this should be working. And this is not working, but this is working. And here we keep the time too. Okay. So we were, thanks for the feedback. Here it is WS for the year 2000, and then we calculate the climatology. Actually, it would be cleaner to see these errors to put year split, for instance, and we put the 2000, and here we have the 2000. So we have here the arguments, and here we have the processing, and here we have the climatology. Okay. Now we are going to see deviation, DTS. Deviation is going to be the opposite. Okay. Actually, I'm gonna the opposite of this Boolean, or let's make it just cleaner. Let's make it like this. Okay. So now deviation will have from the year 2000 to the year 2020. Let's validate it. From the year 2000 to the year 2020. And climatology is before the year 2001. Okay, so now we split it. Great, we are good to go. Now, those are quarters, so what we have to do now is DTF depth dot resample time equals 3 months. And we are doing with median. Let me see if I'm doing properly the resampling before. Yes, I'm grouping 80 groups. So I have 20 years, and 20 years 4 times is 80. We are good to go. Now here we make like median. And looks good. It's thinking, but in the meantime, let's do quarter deviation. So here we have the quarter deviation, actually, and here we have the climatology. Okay, one of the things that we could do now is to let's see how these last 20 years calculate average for every 3 months to be compared with climatology defined above. Okay, so now here you have it. Now let's see how this deviation compares to climatology, and let's see what's been happening in Europe, the entire Europe area, the big picture, for the last 20 years compared to the 20 years ahead. Now, quarter deviation has shape, and we'll see that it is 80, 44, 76 once it is calculated. Yeah. And now what I can do is like a mean in 2 axes. And which axes are these going to be? Since I want just to have a kind of a spatial average, I'm going to take the -1, -2 first, and then the -1, which means that I'm going to average for every latitude and for every longitude, which means that if before we were having a map images, now we are just going to have a time series. There you go. And this time series could be also plotted. And that's the wind average, the wind quarterly average for every a quarter since the year 2020. Actually, we could use these to pull out time from here, and that's an ampere array. If that's ampere array, that's amazing. We have data, so we could just plot the years. Okay, there you go. Here we have from 2004, 2001 going to be the first to 2020. And now what we can do is to say, okay, let's compare this. First, let's make it a bigger figure. Fixed size is like, that's the typical size for Word documents. Okay, it's a little bit bigger. And let's plot here to climatology. Plot. Let's plot the climatology. But this climatology has to be also average. Okay, so we need the same spatial average. Let's set a level, which we're going to call climatology, and that's going to be from 1979 up to the year 2000, and that's the deviation period, which goes from 2001 up to 2020. Climatology, of course, it has, we have to repeat climatology because it has shape 4, and we need it to be like shape 20. So if we go like data, that's an ampere array already. Yes, like ampere arrays, and we make this like we're talking about 20 years, if I'm not wrong. So it's gonna be something like that. NumPy dot concatenate we write it properly, concatenate. There you go. Here we have the climatology. Repeat it. I'm just tricking. Let's put it here. Trick climatology to have same dimensions than, how did we call it? Quarter deviation. So we can visualize. So we can visualize it. That's the goal. And this is climatology to visualization. Climatology to visualization has shaped, I believe. Oops, damn it. Go straight to the point, and it not will correct not will correct it. There you go. Yes. So, what do we see here? Imagine. Blue line, it's always the same. It's always the same. And here we have seen in the orange line that there are deviations for every 3 months. That's actually quite a big average every 3 months. So if you have a deviation of every 3 months, which is significant, it means that there was quite few or more wind. Actually, we could do this for every month. For every month. So here we just write month, and we just get the monthly average. Actually, here we just have to, if that's a monthly average, that's going to be 12 times. Okay, because it's every month, and we could plot the results. Another thing that it's interesting to do now that we have that is to calculate what's the real deviation. The real deviation is calculated by the, let's put the root mean square error, for instance. Let's make a root mean square error, y and y hat, and it's going to be like, so it's return numpy root square t numpy from numpy mean square t. I don't like this thing here, root mean square numpy power. That's this. That's so that's power 2 between I minus I hat. So that's a root mean square error. Yes. Yeah. Here I did something wrong with the dimensions. Let me see. Which is the shape of climate? It's 12, and it shouldn't be this. What's the original shape? Yeah, so my mistake. There you go. Here we introduce more noise if we make it monthly average. So we can just play here, and we can just change between quarter and month and 3 months here. I think great. Root mean square error is this function, and here we can see the deviation. Actually this could be transformed into a percentage, but let's calculate it. In any case, it's the root mean square error between the climatology and between this operation here. There you go. And here we can see the root mean square error in terms of wind speed, 0.27%. That's the deviation. At some point, we can even calculate it like a percentage. So if we want to calculate it like a percentage, we should have to divide it between climatology and in the end I multiply it by 100. Let me just see. Oh, I forgot to add that divide operation. There you go. So that's in percentage. And here, climatology for the sake of visualization. And here we have the deviation. And that's y, which is divided homology. Yes, that's y. Okay, so we could therefore see that for an average of all Europe, there has been deviation. But this deviation is yet, actually we can print this deviation in percentage, is yet relatively small. Let me close here, deviation in percent. This deviation is yet really small, 6.5. And some can say, hey, do we really care about the deviation of wind speed? Is that important? Well, it depends on your investment. In the end, that's the only output that you have. So the output of energy is directly related with wind speed among temperature, but it's not that significant, or pressure. It's not that significant either. So you can even make a linear correlation between your budget, your production, expected production, and your deviation from here. But there is something very interesting too that I would like to talk, which is, since we have this data now, we can even see if there has been any trend, decreasing or increasing trend in terms of wind speed. Like, how will climate change impact on my wind farm if I expect it to make me rich for the next 25 years, at least, for the next 25 years. But what will happen to wind speed for this, let's say, next 5 years? Now, what we have to see is if there is any climate trend. And the fastest way and the cool stuff to see that is that with this equation, y is mx plus n. Anybody knows these equations? This equation? Am I alone, maybe?
No, but I think you lost most of us. We're following along. Linear regression is, I think, pretty much familiar with everybody.
Okay, great, thanks. So that's a linear regression. If I have a negative slope, what will happen is that there is a negative trend of wind speed. So since we already have the data in here, okay, what we can check, let me copy just the names that we have, but what we can check is what has been the wind trend, for instance, the monthly aggregates. Let's make it for the entire time series, okay? So in that case, we will take DTS of wind speed. That's the ones that we want, and we'll resample it directly. So we'll copy this. I'm just copying so I can make everything in time. Okay. So this is my monthly series. And it's calculating now median in dimension time. I think that it was already automatically, it was understanding monthly series. And what we will have now Actually, let me stop it. It's like on the series dot shape. It's like 12 months or 40 years, 160 months, I expect, something like that. Now it's calculating all of this, thinking. In the meantime, the guys who stayed, I guess that you are the ones who are using Python at some point, is it? There you go. 500 months. Yes, we are good to go. We can even plot this. Dot scatter. Let's make it like points. And the scatter plot is going to be like that. And we can see this way. Why it's not the same size? Monthly series is not the same size. Yes, it is. 504. And monthly series data is the same size too. Should be reshaped. Let me copy the average. The spatial average is this operation here. Forgot it. And let's put it here. Now we have the mean. We don't need to extract the data because we're operating, or yes, better. Try with data. There you go. For instance, here, what we can see is that for every month, we have had wind speed that ranges between 3 and 5. Okay, that's the values. And we don't see like a negative trend. Actually, here we could fit kind of a horizontal line. How can we fit this? From sklearn, linear. Did we import this library already? Not to repeat myself. Yeah, we imported linear regression. It's on top. Okay, so we just say, okay, my OLS, ordinary least squares, linear regression. It's this one here. And we say, okay, my OLS, my model, let's call it model, is this one here. Great. My model, I will have to fix what with data and y data. Actually, let's update. That's y data is a monthly series average, and my x data is going to be an NumPy range because we are just taking all these x-axis values. Okay, monthly series, which is already, or let's put it y dot size. Y dot size. Great. So here, what we are getting is for this linear regression, x and y, our data. Just to make sure, let's put it as a NumPy array, not to mix things, and the NumPy range is going to take the size, yeah. And data goes outside. And And here we have the model, and here I forgot to fit it. Now we're fitting. And now he says, okay, reshape it. Let's reshape it here. So let me see the y-axis. Shape is 504. So he's expecting like, because that's a scalar, is number of instances, if I'm wrong, and number of features. So if we go reshape and we say, we could make a variable of this length data, and length data, it's going to be directly the length of this. And now if we reshape it like this, length data, like length data 1, there you go. Here we have it as a scalar wishes. Perfect. And that's my y here. And here I'm going to take this variable, which is going to be used here. And here in my x, I'm going to reshape it to following this formula too. So it's going to be, now he understands that there are features in the dimension 1 and in the dimension 0 instances. Great. So now we fit it. Good to go. And now we can ask the both parameters. I forgot the names actually, which is coefficient, I believe, and intercept. Coefficient, intercept. Okay. Coefficient. Yes, there you go. It has a slightly negative slope. That's M. It has a slightly negative slope. But cool thing could be, do you understand this result? That could be called M. This is what we have seen. Yeah, it could say that, we could say like, yeah, we're losing wind in Europe at some point. Not that much, but it's not 100% horizontal. Makes sense. Okay, for every month, we're losing very few wind. That's what it says. But of course, how much months do we have here? 500, I believe. And actually, the number of months is this one. So this is what we, in the big picture, are losing for this period in terms of wind speed. And this is for the whole Europe, including sea, including land. But we could do a cool thing that it is, okay, what about for every region of Europe? So we have our monthly series here, plt.imshow, sorry, of the 0, the first one. And here we have our monthly averages. But where are we losing wind speed? Yeah, so we want to make a spatial analysis. So where are we losing wind speed? The idea would be the same, just that we have to loop. Let's comment this. So we are not calculating. Let's uncomment and let's go another cell. And the idea is like, okay, let's do the following. For let in monthly series, is it? Let me keep the shape here open. For let in monthly series shape, and latitude is in position 1. And that's a range. So here we are iterating for every left, for every longitude. And that's going to be in position 2. Now, for latitude, for longitude, what we'll have is a monthly pixel, which is going to be monthly series, all data, latitude, longitude. And this monthly pixel is what we could feed into a linear regression. So we can see for every area of Europe, for every pixel we have here, which actually are quite a big pixels because that's ERA5. So that's not the high resolution data that we should be using. But for the sake of demonstration and for learning purposes, it's useful to us. Okay, so here we can say, okay, for every pixel, let's make a linear regression, create new linear regression, create new linear regression. That's kind of the most basic machine learning. It's not even machine learning, actually, OLS, least squares. But in any case, and this linear regression is the ones that have to fit. So this model is created here. Here we fit it, but we fit it with monthly pixel. That's the idea. Monthly pixel, for instance, will be like, okay, for the first month, the 0 and the 0, that's top left, 0 and 0. And this has a, monthly pixel, monthly series. Here's monthly series, yes. And this has a shape of 504, which means we have every month in this area. We're just doing for every area. So we have to reshape it too, as we did before, because sklearn is asking us to do so. And here, length x is going to be always the same. It's the ones that we already generated here. So we could, just to make sure that those processes are independent, we just copy them, okay? There you go. We just copy them. And what we do is the following. The instruction was like coefficient of model. Here we make the fit. And we say coefficient negative. Actually, coef returns a list of lists, so we have to clean it. I would say, let's do it like this. This returns true. Okay. If the coefficient is negative, here we're going to make out analysis, Europe analysis. Analysis, and it's going to be numpy empty. It's going to be numpy empty of shape of the series from 1 to the end. Okay. Let me see if this was directly the shape, maybe. Come on, shit. Now, forgot to put shaper now. And no, we cannot interpret this 44 as data type. So it's going to be from 0. And here we're going to put monthly series dot shape. That was what's happening. in the axis, tool. There you go. Okay, and that's the Europe map. Yeah, that's the Europe map. So that's what we're gonna fill the analysis data. Okay, there you go. Now, if we have in this latitude and in this longitude, if we have a negative trend, what we're gonna do is to trick and say, okay, Europe analysis in this latitude and in this longitude is a NumPy none. Don't fill it, it's negative. And if not, we'll say, okay, in this area, what we have is NumPy mean of the pixel, which is the variable. Here we do a mean because they are already monthly average, okay, no problem. And this is the variable in dimension 1, and we do the mean, and we'll be filling with mean values. So now, if everything goes right, and monthly pixel looks like, let me see how it looks like, monthly pixel, this variable we have generated here. Oops, so we have to say monthly pixel of wind speed, or monthly pixel. And why do you say that it does not have data array? That's data array. We have to do like this maybe. So data reshape, data.reshape, I forgot that reshape. And the reshape that we want to do is this one here with these two parentheses. Yeah. There you go. Now we are reshaping this, just adding data. And here, multipixel dot data dot reshape. Now, model coefficient squeeze. I've got parentheses. Now it's calculating. So now we are generating our European analysis. And let me, in the meantime, close this. And our analysis will look like plt.imshow. There you go. In almost all Europe, only in Spain, we are having more wind, but in almost all Europe, we are having negative trends of wind speed. Actually, we should here use baseband or cartopy, but for the situation, we understand, yeah, this plot of sure. LT title, wind trends, if negative, NT data. There you go. Does it make sense to you, this? Are we good to go? Would you imagine that wind speed is decreasing, maybe slowly, maybe faster in all Germany and Italy? Only in the Alps is growing, and in Spain and this part of Africa, actually, and maybe in the north. Well, in any case, let's move forward. Just to finish, a very quick demonstration that I believe that after all this learning, it's going to be even you could do it yourself, okay? But a
quick question, if I may.
Please.
So now we calculate the median wind speed or the average wind speed going down. But from my understanding of what I learned about climate change is that it's mostly the change is going to be that we are going to have longer periods of identical weather because of the jet stream breaking down and stuff, right?
Mm-hmm.
So we are going to have longer periods of heat and longer periods of drought and longer periods of cold and these things. So instead of days, we're going to have months.
Yeah.
Right? Yeah.
Yeah.
So then wouldn't we need to get an accurate picture of the wind revenue, do a filter for minimum and maximum wind speeds that are actually useful for wind turbines first, and then only look at the times when the wind turbines would have run actually? So
that's a very good point. That's a very good point. Interesting. So you say instead of looking to trends, try to look what is happening in given periods.
Look at actually usable energy per month.
Yeah, that's a very good question. So this should be done too. Of course, here we are just making quick demonstrations.
Yeah.
But at some point, this number here is a correction factor that you want to put in your budget if you want to invest in a wind farm. You know what I mean? So the utility of this, what you say is true.
Yeah.
And actually, a lot of analysis should be done, and not with this 30 square kilometers pixel size. That's a 30 square kilometers. So microclimate effects are not represented in here. So that's we're losing information. But what you say is true. But what at some point what we are showing here is like that's a correction factor that you could take into account for your planning for the engineering department. Yeah. From here, of course, you don't want to work with historical data only. You want to work with projections. But that's also another story. I mean, so far we are just having one data set and validating what is happening. So what I also showed here that could somehow answer your question is like, look, if I just take a methodological year, I'm good to go. Because there is a deviation of 6% maximum, which is those bottom points here, those maximum points here. So I'm good to go. Just a deviation of 6%. They say, Joan, come on, dude, don't bother me. But it's not only this. It's also that you are not assuming that it can take consequences from a trend point of view. And also from here, you also should be looking in micro scale, if you can, with every 10 minutes. So 10 minutes average for this typical year, what's the behavior of wind speed and how wind speed is sustaining or it has been sustaining in the study area. It's different ways. This data set is every 3 hours. I think that the highest resolution that you can get is every hour. So you cannot use it for on-site project management of wind farms as it is. Do I answer your question?
Yes, thank you.
You're welcome. But very nice contribution. Thanks a lot. We've got 5 minutes left. Is there any other question so far? I think we can rather talk about different topics. And if not, since 5 minutes it's not time, I can tell you what happened here with soil radiation. So just introduce it. Actually, I believe, do you see that I'm opening a new collab here? I believe that it was like down here. Yeah, look, with radiation, that's the same, that's with radiation. What we have is a deviation of 15%. So that's not even a matter of climate change, not climate change. That's even a matter of people is planning solar parks looking at this map. And they say, oh, here, that's perfect. And they put the point here. But with wind speed, there is actually less uncertainty on the meteorological year climatology. There is less even uncertainty with wind speed than with direct normal solar radiation. This is, of course, the most complex variable in terms that this is the direct one, which means that your surface is mobile. And I'm calculating here, if I have the sun incidence is from here, my solar panel is going to be switching. So every time there is a normal between the sun beam and the solar array. So yeah, that's the most sensitive. But with this other data set, what you can see is that the deviation is about a 15%. Actually, let's make it and here. BNI is the name of the variable. In this case, dataset should be opening the file that we have here. Let me see. How did we call it? In files. Yeah, it's in files. In files .0. No, it's not .0. Come on, it is -1. This is the last one. So it's in files -1. Here we split to get the typical year. Here we have it. So that's a plug and run. And here we calculate. So with solar radiation, it's insane because money was flowing, and I believe it's still flowing from banks because they just say, hey, look, I've designed my solar park for this area here in Spain. So I'm going to have whatever. But every year, 15%, this can hurt. And this can hurt a lot of your budget. That's significant. And that's all. Any question regarding solar radiation? I just made the same. I just made the same here. It's the same process. Is there any guy designing solar here or wind farms? Any of the here? Oh, I didn't see. If you can zoom, it would be better. I could not see that. I didn't see the chat because I was sharing a screen. No, did you find it useful at least? Did you find it interesting? So we somehow demonstrated from a statistical point of view the impact of climate change in renewable resources, and that was the goal, and not to talk just about climate change is happening, look at the temperature, or no, like, hey, it's not only about this, it's also about the industry, and the industry is not concerned about the temperature. It can be concerned too, actually, but solar radiation and wind speed, those are other variables that we should be taking into account. Benedict, thanks a lot. Thanks a lot for your comments. And Johannes, thanks a lot. Yeah, notebook. Session is finished, guys. I'm gonna download the notebook and upload it here. So if you want to move to any other session, feel free. And let me just
Thank you.
my pleasure. Any question, you can find me in LinkedIn. Okay, I'm gonna type my name, so feel free to Joan Salavic in LinkedIn. And here I'm gonna update upload